Hello everyone, welcome to TriTea. Today we're going to solve two interesting problems, step by step. So let's begin with the first one.
Imagine inviting a friend over to visit. You wouldn't physically pick up your entire house and move it to their location. You'd simply write down your street address on a piece of paper and hand it to them. A computer works the same way. It stores information in temporary memory, which we can think of as a giant city. Individual pieces of data, like a character's health in a game, are like houses. Standard variables are the actual bricks and mortar holding that data, but we don't always want to move those heavy bricks around. Instead, we use a pointer. A pointer is just a piece of paper that holds the house's address. It points to where the data lives, without being the data itself. This diagram from our technical guide shows the system in action. The variable p is our pointer. It doesn't contain a letter itself. It simply stores the location of the character C sitting further down the street. Using these addresses means the computer stops doing heavy lifting. It navigates through its memory city instead of constantly rebuilding houses in new locations. This efficiency is vital when things get crowded. Imagine a program needs to take a list of 10,000 items and pass it to a new department to be processed. Without pointers, the computer has to clone the entire list. It painstakingly copies all 10,000 items into a new part of memory. This takes up twice the space and keeps the processor busy with repetitive grunt work. With a pointer, the computer only hands over a single address, the coordinates for the front gate of that list. By using these shortcuts, the computer moves with much less effort. It functions like a scout rather than a mover, finding exactly what it needs in a fraction of the time. Once we understand individual houses, we can look at larger structures. An unbroken row of these data houses on a single street is what we call an array. In C programming, an array's name is actually a pointer to the very first house. Because these houses are perfectly aligned, we use simple math. Adding 1 to the pointer jumps to the next house. Adding 2 jumps 2 down. The computer never has to search for the next house. It calculates the destination instantly because it knows exactly how far apart the houses are built. This combination of organized streets and instant navigation makes for a very predictable neighborhood, which is the perfect setup for high-speed searching. Even in a perfect neighborhood, we still have to find who we're looking for. How do we find one specific person hidden inside one of those houses? A linear search is like a hallway of lockers. You open locker 1, then 2, then 3, until you eventually find the right one. This works for a small, messy pile of data, but as the amount of data grows, this method becomes much slower. If your target is in the millionth locker, the computer has to make 1,000,000 individual checks. Brute force eventually gets the job done, but it's an inefficient way to run a city. To go faster, we use a strategy called binary search. It's a method that relies on dividing and conquering. Imagine looking up a word in a physical dictionary. You don't start at page 1, you open to the middle. If your word starts with B and you're on the M page, you know it's in the front half, so you can throw away the entire back half of the book. You just keep splitting the remaining pages in half. Every step removes half of the possibilities until the word you want is the only thing left. This code shows the math behind that split. By checking if our target is higher or lower than the middle house, the computer knows which way to turn. But this only works if the street is perfectly sorted first. When the data is in order, we gain the ability to skip almost everything in the search area. To see the payoff, let's look for one specific item in a list of 1,000,000 items. A linear search might take a full 1,000,000 steps, but by cutting the list in half over and over, a binary search finds that same target in just 20 steps. Pointers and arrays provide the blueprints for the computer's memory, and algorithms serve as the GPS. Together, they give the computer a clear sense of direction. Programming expertise comes from knowing how to instruct a computer to navigate its map, rather than asking it to carry the weight of all that data on its back. And programming logic remains a constant across every environment. While the syntax you type changes from one language to the next, the underlying reasoning is universal. We are applying that universal logic to the majority element problem. In computer science, a majority element is any value that appears in a dataset more than half the time. meaning its frequency is strictly greater than the total length of the array divided by 2. To find it, visualize this array as physical real estate. If one color occupies more than 50% of the total space, it dominates the sequence. Currently, those elements are scattered and disorganized. When we group identical elements together by sorting them, the dominant group becomes a solid block. Because it owns over half the space, it has no choice but to overlap the exact mathematical center of the array. We solve this by exploiting spatial positioning. In a sorted list, the element that occupies the center index is the guaranteed majority. This spatial logic translates into a 3-step algorithm: sort the array, calculate the middle index, and return the element at that position. Even though the logic is powerful, the actual code required to execute it is very brief. Let's walk through a dry run using a 3-element array: 3, 2, and 3. In most programming environments, we track these positions using zero-based indexing, labeled here from 0 to 2. First, we organize the sequence. After sorting, the blocks read 2, 3, and 3. The data has moved, but the index positions remain fixed. Now we calculate the middle index. Our total length is 3. Using integer division, which discards the decimal, 3 divided by 2 gives us an index of 1. Finally, we look up the element at index 1. The value stored there is 3, which is our majority element. By combining the rules of zero-based indexing with integer division, we always strike the mathematical center. This eliminates the need to manually count occurrences. Now you act as the compiler. Process this next dataset using the exact steps we established. Here is your target array: 2, 2, 1, 1, 1, 2, and 2. It contains 7 total elements. Pause the video here. Sort the data, find the length, divide by 2, and identify that middle element. Manually stepping through these instructions is the exact process a computer uses to execute your code. Let's check your work. The dataset has 7 elements. Dividing length by 2 gives our middle index. 7 divided by 2 is 3. Next, we sort the array. 1s move to the front, 2s to the back. At index 3, the value is 2. This workflow serves as your reference for the majority element problem. Identify the goal, sort the data to force the majority across the center, and return the value at the middle index. This logical sequence, sorting, calculating length, and index lookup, is a universal blueprint. Whether you use arrays.sort in Java, pointer-based sorting in C, or built-in list methods in Python, the machine executes this exact identical thought process. Master the logic, and the syntax will follow.
Now let's see how the code looks in C. in Java. Let's now move to the second one.
The logic you use to solve algorithmic problems is universal. It doesn't matter which programming language you write in, the underlying math remains the same. Our goal today is to solve the three-sum problem, finding strictly unique triplets in an array that sum to exactly 0. A common naive approach is to use 3 nested loops on an unsorted array. 3 random numbers attempt to sum to 0, fail, and force the computer to guess again. This results in inefficient performance because the computer has no logic to guide its next choice. To solve this, we must first sort the array. When the elements snap into numerical order, every number is now greater than or equal to the one preceding it. This creates a predictable environment where we can apply a specific search strategy. Within this sorted array, we use 3 specific points of reference. We lock the first number as our anchor pointer. Then, we place a left pointer immediately next to it, and a right pointer at the very end of the array. Using 3 distinct pointers on a sorted dataset gives us a framework for a systematic search. By holding the anchor steady and moving the other 2, we can navigate the array based on the values we encounter. With the array sorted, our pointers gain logical direction. If the sum is too low, shift the left pointer right to increase the total. If too high, shift the right pointer left to lower it. We adjust inward until landing on a perfect zero sum. This directional movement takes full advantage of the sorted data. It ensures we find valid sums while skipping millions of unnecessary combinations that a random search would have to check. A common reason solutions to three-sum fail is the presence of duplicate numbers in the source array. If the algorithm processes the same values twice, it will output the same triplet multiple times, violating the requirement for unique sets. Consider our pointers as they slide across the array. If the number directly next to your current pointer is identical to the one you are already on, what must the algorithm do to avoid recording a duplicate? We must skip over them. The pseudocode shows how we use a while loop to move the pointer past identical adjacent numbers. This logic applies to both the anchor and the moving pointers. Skipping duplicates at the pointer level is the specific mechanic that ensures every set in your final output is strictly unique. To see the logic in action, we'll perform a dry run. We lock our anchor at index 1 on the -1. We place our left pointer immediately next to it and our right pointer at the end of the array. We calculate the sum for these 3 positions. -1 plus -1 plus 2 equals 0. We have found our first valid triplet. Next, the pointers slide inward to search the remaining values. Our logic skips the duplicate -1 and lands on 0 and 1. This second calculation, -1 plus 0 plus 1, also equals 0, giving us another valid set. This graphic contains the complete, language-agnostic three-sum pseudocode. It summarizes the sorting, the pointer movement, and the duplicate skipping logic in one place. Because this solution relies on fundamental array manipulation and sorted data logic, the execution remains the same whether you implement it in Python, Java, C++, or JavaScript.
Now let's see how the code looks in C. In Java, in Python, Comparing all three languages, C, Java, and Python, we can clearly see how the core logic is same in each three. Just syntax is the one which changes. Thank you for watching. See you in the next video.
Subscribe now.